Hello, good evening.
Good evening.
Yeah, good. We got audio. Cool. Um, I'm, I'm writing down the notes we're going to do today. Screen number control. We build a grid. Okay, I'm not talking yet. That's why you're not hearing anything. So don't get all freaked out. I'm checking. Okay, nothing from Jawad. So we're just waiting on him to connect. And yeah, my microphone seems to be making noise. So I got to remember to talk loud enough so y'all can hear me. Otherwise, I have to put the headphones in my head, and that I feel like I'm talking in a bucket when I do that. All right, I'm going to go ahead and proceed. And if Jawad joins us midstream, we will catch him up because he'll have the video. And actually, this video is going to go to another, it's going to reference another video. So today we're going to do the first installment of Storm. And there's a lot of different windows that are open on my computer. I will try not to confuse you, but I need them around because it took me a while to find the missing files. So I'm going to demonstrate the simulations on a Windows 10 machine at my own machine. I'm not going to attempt this on Amazon Web Services. there's no hardware reason why I don't want to do that. As I explained last time, it's a it's the way I've set up the service with them, and I love you all to death, but it's not worth it to me to change a business arrangement just to demonstrate a piece of software that if you have to use it, you're going to do it on a dedicated machine anyway. So with that lead in, let me get you all familiarized with where we're going. So here is Blackboard, and one of the, oh, it's doing its cute thing. One of the content links is the one that was called IRIC tutorials. And in that, there was it took us to a directory. And inside that, there was a data in lecture directory. And remember, I went to IRIC 2008, and then I went to IRIC 2011. Well, in IRIC 2008, there's two zip files. One is called stormtutorialdata.zip. You're going to want that. So you, and the other one is called stormtutorialdocumentation.zip. I think you'll also want that. Before you download them right now, unless you've done it already, then don't worry about it. These two are those expanded. And we'll look at modeling primer a little bit today, and we'll do tutorial number 1. And the reason you need me to walk you through it is the tutorial number 1 is dated around 2009, and the software we're using is dated around 2013, and the interfaces have changed, but none of the documentation's changed. That's that whole Japanese English thing. So if you can't figure it out in Japan's mind, we don't deserve to operate it. That may not at all be true, but so, and then the other, the tutorial data.zip, if you unzip it, you get this directory. And we're going to do the Green River one. And inside the Green River one are, there's not very, there's not a whole lot of files in it, which is all we need for what we need to do today. Okay, so now to download the directory, you would save link as onto your machine, and then do the tutorial. Again, save link as, and depending on your network speed, it should be pretty quick. Because it's a zipped file, it gives you the file size. So you're looking at about 150 megabytes download. So if you're going to do that, I will wait for you to do that. And while your network is doing it, I will bring your attention to another location. I'm going to put that link into the chat box. So if you choose to, or more importantly, copy that link, in that chat box, it goes to a prior year version of this class. And in that prior year version of this class is a video file called Storm Experiments. I'll click on it at the risk of having everything.
Okay, cool.
So
and then let me get decluttered here. And
is it making noise?
For today is, go ahead and get my drawing.
Okay, so you can watch. This has experiments with the Storm program from about a year ago. That was 18. If you go to 19, there is a tutorial, which I think is what we're about to do today. These are streaming from my office computer in my office. Don't think I've uploaded these to YouTube. And the reason why I don't think I've done it is that right there. They're over 1 gigabyte. And to do that, literally, I'd have to download it to my house and then upload it to YouTube. And this little computer that's on right now is more than capable of streaming to the 4 of you all. So watch those if you're so inclined. But we will try to replicate that. I'm sure my vision at the time when I made those was that I wouldn't do anything. I just said, go watch the videos and we'll call that a week of class. But we're not going to do that. My vision is to have everything RoboProft, and all I have to do is manage the class, and then your robot can go take the class from my robot, and everybody's happy, except for the robot repairman, because if you don't have robot insurance, it's like when your car breaks down. Okay, so on my computer, let me get up a few levels. So I created a file on my computer in Win10 ce5362 virtual machine data IRIC files. And in that, I created a folder that I named 54.243.252.9 / lesson25. And those numbers are just a reminder for me to tell me that I took that from a website. And that's the URL to the website. And obviously you have to know the structure of the website to get to it. And inside that are the 2 zip files that I downloaded. And then to expand the zip file, you will right click on it, choose extract all, and it will give you the option to extract, and it just extracts in place. Now I've already extracted it, so I'm not going to choose extract. I'll choose cancel. And then there's one called tutorial data. Right click, extract all, same process. And when that's done, you should have these 2 folders here that have the same name as the compressed files, but obviously they're uncompressed. And I'm now moving into the one called tutorial data. And we're gonna do today, we're gonna do the Green River tutorial. And when you expand it, my projects doesn't exist. So I created that earlier today just to be sure I had working backups. And these files do exist. So before we read the modeling primer, let's files that have the extension .tpo in this particular software environment are called topographic files. They're just ASCII files. I'm just asking you for it. And I'm going to open it with a text editor, if I can find one. Word. I want Notepad, I think. It begins with the letter N, somewhere between news and notes. There we go. And so, just so you understand the file structure, this file has 43,008 records in it, and the records are orientated as UTM northing. Yeah, I think I got that right. I think it's northing and then easting. So that's a coordinate system. That's like an X coordinate and a Y coordinate. And from your GIS classes, a UTM coordinate system is not unusual to you. The reason that UTM systems are preferred in this kind of modeling is until you get close to the North and South Pole, UTM panels are roughly orthogonal, so they roughly have x and y coordinates, and roughly enough that you can pretend that that's the case. And the third column is elevations in meters. It's got to be meters above datum. So that's what a topographic file looks like. And we'll go ahead and we'll look at a picture of it in a minute. The water surface 400 ANC, I'm not sure that that's readable as a text file, but it will have a similar structure if it is. It's giving us the water surface elevation at a couple of locations. So it's 645, 107, 447, 4612. The elevation's 1,447 meters at 645, 535, 447, 3630, 1448, and so on. So these, you can think of these as point locations of known water surface elevation. Now, this file is a tagged information file, tagged image file. So I'm not sure what I can open it with. I can open it with the software, but I'm seeing if I have anything. Oh, what's the worst that can happen? So that file is an image file. And so this area that we're about to simulate is Green River. It's somewhere in Utah. And I'm going to draw a marker on it. That's the flow direction. So it's flowing this way. Everybody see blue arrows? Okay, we're going to examine this region right here in some detail. And some important features are that there's this island in the stream. Oh, you can make a song like, oh, it's been done. You can have this island in the stream, and so the flow splits. Let's pick a new color. Because everyone knows that, there we go, that's a better color. Flow splits like that. And we can't simulate that using a one-dimensional modeling tool. Now we could, to some extent, fake it using our swim tool, because we could define a computational cell like that, cell like that. These are supposed to be rectangles, but I'm having trouble today. And go ahead and build the conduits that way. But this particular tool is for when you don't want to fake things. If we're very interested in small scale resolution around this island. Oh, cool, it does have go away. The reason I'm doing that is in case it saves back to it, I don't want to damage my file. So that's an image file, and that image file plays the same role in this programming environment that our backdrops played in Swim. It's just a picture. It's a little bit more complex than in Swim, because for this picture to render correctly in the modeling software, it has to be correctly georeferenced. Since I'm not a GIS person in any way, shape, or form, I use these without, if I don't have an image, I'm not going to go to the trouble of georeference because I don't know how. Okay, so that is to get us started. And over here, where my finger is in the little viewfinder, where you should see my shining, smiling face. We're at this step. We've just done the get files step. So to everybody that's going to attempt to follow along, get the files. There's only 3 of you, so yeah, either 3 yeses in the chat box, or I haven't started yet, I'm just going to watch you do it. And either of those is fine.
I couldn't find it.
Okay. Let me go back and walk you back through it again, because I'm pretty sure it's there, but not there. I want to go to Firefox. I want to go to that Firefox. So start off in Blackboard.
Oh, Blackboard. Okay.
Go to IREC tutorial, and it should take you to this web location.
Okay, got it.
Got it? Data in lecture, IREC 2008. And then you want to right-click, save target as, the 2-zip files. Right-click, save target as. That should get it to your machine.
Got it, downloaded.
Then you need to extract those, at least extract the data one. You can extract the documentation later. But put it somewhere where you want it. And I have done this with the presumption that you already installed IREC software. Okay, I'm returning to my Windows thing. I will be going slow enough that you're not in any way, shape, or form going to fall behind as you're extracting it. So when you extract yours and you go into the, you go into the tutorial data folder, tutorials, and there's tutorial 1 through 5, Green River, Colorado, Trinity, unstructured, Coeur d'Alene, Utah, probably Arizona, Northern California, don't know where that is, and Idaho. We're going to do tutorial 1. I went ahead and created a folder called My Projects. I will go ahead and go through the steps again. I'll have a different, I'll call it my newer projects or something like that. In my projects, I have a few simulations already run. The reason I did that is once we get past the initial designing and building of the computation grid, computation takes a long time. At that point, I'm going to go to one of these runs and I'll just show you what the output looks like so that you don't have to wait 40 minutes for results. But we'll do the initial runs as if we're going cold. Okay, so there is our tutorial. In the tutorial documentation, there is a modeling primer and the actual tutorial 1. So let me go to the modeling primer first. And that's right, it doesn't want to open anymore. Okay, so that should be readable, and you can read this on your own. I want to scan through it pretty quickly. It tells us what the acronym means, transport river modeling. And it states the obvious. So obviously this is written by a PhD. We use software because you can't do it for real. Then it has the usual tutorial stuff on the wormhole that is modeling. So keep in mind, I don't know if you guys are Star Trek aficionados, but computer modeling and wormholes have an awful lot in common. You usually lose your warp drive at some point when you enter that wormhole. And then the authors of this go on to describe the underlying equations called Reynolds average, Navier-Stokes. That's actually what we've been using already. But once we go to higher dimensions than 1, all of a sudden some other forces come into play. Gravity was in play before. Buoyancy we didn't think much of, but it was there before. But now Coriolis plays a role. And the Coriolis force is the force that a spider experiences when it's on a turntable. And the turntable is spinning around as the spider walks from the axis of rotation out to the edge of the turntable. As far as the spider is concerned, it's walking straight, but as far as we're concerned, it looks like a drunken spider because it's spinning all over the place. And those Coriolis forces, if you get far enough away from the axis of rotation, start to have some significance. So the Coriolis force at the equator is relatively small on objects that are flowing. But as we move away from the equator, we're actually moving closer to the axis of the Earth rotation, and Coriolis forces start to play an important role. And I'll refer you back to your fluid mechanics class for that. It was in the lecture in fluid mechanics where they introduced Reynolds average Navier-Stokes and then moved on to something else, because nobody teaching fluids to sophomores and juniors can take the 2.5 to 3 weeks to go through the calculus that's involved. So we blow it off. But like we did with the St. Bernard equations, we have an expression related to velocities, and now instead of one direction, they're in two, the x and the y direction. And when we get done, we get a momentum term. I really wanted to highlight. I don't want to cut and paste it. I guess I don't have a choice of highlighting. So we'll look at this first one. If we recall our our St. Bernard equations, so this d times u is like a flow rate, a q term. So that the rate of change in velocity with time plus the convective acceleration terms is equal to the sum of the forces minus some force due to gravity, and then this stuff here is our frictional forces. I'm oversimplifying it greatly, but that's all this equation is. So we've seen a version of this equation early in the class when we reviewed the St. Bernard equations. What makes it more complicated now is we're in 2 dimensions, x and y, and I guess three dimensions if you count time. So time, x and y, and then d is our flow depth. Oh, don't go spinning beach ball on me. And here is a sketch of a computational cell. So there's the elevation at the bottom of the cell. There's the flow depth at some instant. So this d can go up and down. In our development of St. Bernard equations, we either use the variable h for depth, or I was using z, but doesn't matter, any letter of the alphabet that's convenient. And in this case, there is a direction labeled u, which corresponds to the x-axis, a direction labeled v, which corresponds to the y-axis, a direction labeled W, which corresponds to the up-down axis, and then we have a net velocity vector, which is shown here as U with a vector symbol, which is comprised of the three components, U sub x, the U, V, and W. The necessary complication of computational fluid mechanics is the use of lowercase and uppercase letters to mean localized and integrated versions of the same thing. In the convention, the U is velocity in the x direction, V is velocity in the y direction, W is velocity in the z direction. Capital U, written as a vector, usually implies the net velocity vector, which is comprised of those three components, U, V, and W. It confused me for years, and at some point you finally just learn to live with it, because the geniuses that do this aren't about to change. Part of me thinks that sometime in the past they did that on purpose as sort of a price of admission. So that's a complicating thing that will come up from time to time. Then they equate the various stresses in the system to this equation here, which has stresses related to viscosity. That's what this little deal is. And then stresses related to various turbulence terms. In the St. Bernard equation, we were able to take those shear stresses and essentially push them all into a Manning's equation type thing. In the multidimensional ones, that's not always done. Here they have some additional, let's call it a simplification for lack of a better name. And at some point they get to the turbulent bottom stresses in the x direction, turbulent bottom stresses in the y direction. These played the same role that Manning's end played in our one-dimensional cases. And in fact, they actually use Manning's end type structures. So note that the bed shear stresses can also be written in terms of Manning's roughness coefficient or Chezy's C. And they show how to make the changes right here. So at this point, right now, an incorrect mental model that nonetheless is useful is you can think of, we have a Manning's end in the x direction and a Manning's end in the y direction at each point in the computational space. We actually don't. Manning's end doesn't have a vector property, but when we multiply by the localized velocity vector, divide by the cube root of the flow depth, and multiply by gravity to get a shear stress, it takes on directional information conferred to it by these velocity terms. So we did a lot of one-dimensional models that are cross-sectionally averaged and so on. And now we're moving into higher dimension. So in the higher dimensional models, we're going to use Lax's scheme again. Actually, the computer program is. We're not going to do squat. We're going to put in pictures, and it's going to work for us. And then it breaks things up in a finite difference formulation. So that should look somewhat familiar from early in the class. And they mention the same thing that we mentioned with the Lax scheme, that there are different ways of representing things by difference equations, and we can take advantage of them depending on the rate of what things are changing. Now, when I contributed on that paper on the confluence of Houston and White Oak Bayou, At the time, we were working in this right picture. We were using something called sigma stretching, and the reason being is it let us take the physical domain, which had curves to it, I mean, stuff was bendy, and map it into a nice, comfortably happy rectangular domain. And that's what we'll use the software to do tonight. We're going to produce grids that look like this right picture, all sort of distorted. What's happening inside is a conformal mapping to get everything onto a rectangular grid, and then that's where it does the computations. The other way to do it is to just superimpose the rectangular grid on the physical domain that you want, and that's perfectly adequate, but it gets a little bit challenging when you get things that look like that. Because imagine trying to represent this coastline with a rectangular grid. Having the rectangular grid change size, that's not a big deal, that's trivial. But having it follow these curves is challenging at best. Because you want to use as big a rectangle as you can, but if we want to stay faithful to the shape of the coast, we have to get small in areas of high curvature. So the alternative is to map everything with triangles, which have a little bit more flexibility and an ability to follow curvatures. So that's what this picture is trying to tell us. And then there's different kinds of small elephants, finite elephant modeling. And STORM uses a third thing called a finite volume method, where when we generate our grid, we're actually creating a control volume. A control volume is not at all unlike a storage element in SWIM. I dare say it's probably almost the same kind of thing. Unlike SWIM, however, if it's this picture on the left, for instance, we are by default 1, 2, 3, 4, 5. We're default connecting 6 conduits to that, 5 conduits to that object. They actually can't go across the corner. That's if we're doing a cell-centered approach. The other one is to work along the edges, and in this case, the cell is defined by its polygon nodes, and the equivalent of a conduit is across the cell face. Now, I'm pretty sure that STORM uses this right side picture because it was built by highly trained professionals, and the right side picture is preferred when it comes time to doing generalized fluid mechanics. If we were writing our own codes in Python, and we only got 2 weeks left, so we're not going to do that, we would probably start out with this left side picture. And that's what I showed on Monday's class when I had the 3 staggered grids. The left side picture is a more natural starting point. And I wish I could say it's trivial moving between the left side and right side picture. I'm going to say it's not that hard to do. If you could get it working in the left side picture, it wouldn't be much of a leap to get it to render in the right side picture. But if you get it working in the left side picture, you're going to be exhausted. You're not going to want to do any more work. I got my numbers, we got paid, we're done. So the attractiveness of a finite volume method is that the spatial discretization is done directly in the physical space. That can't be overemphasized. I got to get some water. I'm choking up. I'm so excited by this. And then the primer goes on to talk about the data requirements, and we'll see those shortly. Here's the area we're going to study in the Green River model. So all these little dots, it looks like a picture, those represent individual elevation survey points. And if we're to focus on, can't quite figure out where in the right picture the left picture is. The way we do 1D modeling is we usually do cross sections. So I'm moving from the upstream in this left picture. We have these cross sections as we move down in one dimension. When we go to higher dimensional modeling, it's actually preferable to have scattered measurements all over the computation domain. So here we see something that looks like the left picture in these main channel. There's clearly transects that are crossing this channel, and then there's a diagonal and another transect and a diagonal, another transect. And so it's likely that those data were obtained using a acoustic Doppler current profiler towed behind a kayak. It has a GPS thing on it, and the kayak person is getting paid to kayak a river. So that's a cool thing. And they're towing this little boat behind them. I'll dig a picture up on the internet in a second. And it's automatically making measurements. It's kind of like your cell phone. It knows where it is every few seconds, and it records that. And that's how all this blue stuff was obtained. And then the green dots, the orange dots, and the red dots are probably obtained from differential GPS, taking an instrument out there, putting it on station for a few seconds. It finds where it is, and then you move it. So all this cool stuff. When I went to college, we couldn't do this, not because we didn't know how, but the ability to get the data didn't exist yet. Because these things require so dang much data, doing a survey of this magnitude back in the 1980s, when I went to college, would have probably taken several years and a fair amount of cash. Now it can be done in a few days, maybe a few weeks at the most, and still takes cash because of inflation. But it's all a matter of having the machinery and being able to put a work crew out there to operate it for a 2 or 3 week period. So it's a real revolution. It's really kind of cool. Now let me see if I can get you a picture of one of these data stations. Oh, that's embarrassing. Acoustic. Let's see what we get here. I'm trying to get an actual picture of one. It's not a very good picture. Oh, dang it. I have access to one out in a laboratory at Texas Tech, but I don't happen to have a picture of it. That's kind of embarrassing. Who's mine following? Mine is, I think it's in situ. Duh. I'll show you what those data were collected with if they have a picture of one. So the actual instrument isn't very interesting. It's something that looks like that. These circular eyeballs, if you will, are where it sends ultrasonic pulses out and then receives them. So they actually are like eyeballs. They are its sensing, there we go, Sutron. Why couldn't I remember that? So here's the one that I have in the lab. This is, see, there's what they look like when they're configured. So this is the current profiler. This little blue thing is one of these. And then it's towed behind with you tie a string to that, to your kayak. And then this is also, this is where it's squirting down the information. And there's a GPS in this blue box and a data logger and a big ass expensive battery. So here's one in action. And here's probably what was used to get the Green River data. So same basic technology as I showed you a picture of, but you notice it's remote controlled. So not only did they not have to kayak the river, they got paid to play with a remote controlled toy speedboat. How cool is that? You will be wishing you did that at work someday, all of you. Those people are getting paid to do this stuff. Now, they're doing it mostly to collect information on the nation's resources, but also to collect the skill so that when the Great War with China and Russia happens, they can load these things up with chemistry that goes poof and go driving it up to downtown Minsk and go into the storm sewer and blow up whatever they blow up when they do that stuff. So here's a picture of me back when I could operate one of these things. Those two gentlemen are not myself, but I have gone on scuba to drag early versions of these things out into the ocean. And what these two particular scientists don't have, I guess they hid it for the picture. You notice you don't see their net bags and their spears. Because when you're doing this, at least in the ocean, and you see a really good fish, you want to like get dinner. So as long as you have your fishing license, you can keep your spear with you, and it's just a fraction of a moment to spear the fish, put it in the bag, and then go back to doing science. Because the key thing in science is to be able to do other parts of living. So that is an acoustic flow profiler. That's how all these blue lines came about. A flow chart to tell you how expensive this will be. So when you're going ahead and preparing a project proposal for a client, you can simply provide this spreadsheet and say, we can do that. And they'll go, how much does it cost? And you go, each step is $125,000. Well, of course, that was years ago, probably up to $250 now. This stuff is not that cheap, getting the data. And then it goes on to describe the actual software. And we're going to ignore this because this is all the wrong interface. So let me close the primer. We're going to go do, so I just wanted to give you some background that they didn't completely pull this off of the internet and make us think that it's actual science. Oh man, I don't know how you Windows people can put up with this stuff. It resizes when you don't want it to. It moves where you don't want it to. The only thing worse are Apple products, which do all the above. Okay, so we're going to go ahead and build a model of the Green River using the surface water modeling system, which we all have downloaded and comes up as the IRIC modeling software. And I'm going to work through this tutorial. I'm going to skip one component of it. Let me get down to the component I'm going to skip. I'm going to skip the part where we put the island in. I'll do that today, but our first one, we're going to try to just build it and get it to run. So I'm going to skip the part where we put the island in. The other thing I'm going to do is, as I'm going through this, I'm going to point out the differences. Because, for example, these particular dialog boxes don't appear that way anymore. Okay, so the steps for preparing the data are reading the bathymetry and then processing it, building the grid, entering the minimal parameters needed to run the model, and those are boundary conditions and friction, picking some reasonable values for some of the time stepping stuff, running the model, and visualizing the results. The downside is that at least the version I'm running is supposed to be able, you're supposed to be able to take the output from one model and use it as an input for another model. That doesn't work. It just sort of stares at you like you're stupid. But the intent is, in practice, finding the best model results requires multiple model runs. It's a fancy way of saying keep showing it to the client until they look happy. That's mean of me. Usually you can't get this to produce meaningful results the first time out the door. And that's just the way it is. So what we're going to do next is, let me get my green thing, because everybody's had time to get their files. I'm going to start IREC next. So that's really hard. I'm just going to click on it. Hopefully it'll come to life. Okay, so I'm not going to open these projects. Those are for an emergency if everything doesn't work right. We're going to create a new project. So I click on Create New Project, and in Create New Project, it asks you, what fancy bit of software that's built in do you want me to use? And there's all these different ones. Today we're going to use Storm. And it implies that you can type a description, but you can't. And it's supposed to tell you what the license agreement is, but you can't. Choose Okie dokie. So I've picked Storm, and now I have this pre-processing window, and I'm just sizing it to make better use of the real estate. So the first thing we need to do, according to the thing, is read in the bathymetry, which means we actually have to have bathymetry data. So we're going to go in the Green River tutorial, and I'm going to navigate to the .tpo file in the import delimiter up here. I believe you can also do it from File, Import. This particular software interface has about 100 ways to do the same thing, and in some cases, some of them don't actually work. So we want to pull in elevation data. So if I click on elevation, it's going to ask me what file do I want to import. So I'll go to Green River, I'll go to my tutorial data files, I'm going to grab gr.tpo, which I assume means Green River topo file. Choose open, and then it's asking me if I want to filter the data set. I go, oh, whoa, what's that mean? So let's read what filtering is. The user is prompted for a file name. Upon successful selection, automatically triangulates, blah, 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 blah. And I have not experimented with what increasing the filter does, but I think it skips a certain number of elements in the irregular triangular network modeling tool, but we're just going to take the default, which is okay. And so now we've got pretty pictures of points. The wheel on the mouse zooms in and out, but there is no left and right. The way you pan is you have to use these stupid arrows up here. up and down. You also can use the plus. And I think I'll leave it at that scale because that should work out for later on. We can suppress the points by turning them off. They're still there. Off, on, off, on. You could also leave them on. You can suppress elevation off, or you can just turn off geographic data. Okay. So at this point, it's a good point to save as a .ipro project. So in this thing, it says this first save is actually unnecessary. It's just creating a place where we can do it. So we'll go ahead and we're going to do save, and I'm choosing save as. And I'm going to go back to, I'm going to create a new folder. My other projects. I don't like that name. I'm going to do it my, how about in class? That seems like a cool name. So that's my attempt to do it live. Keep in mind I have this my project directory is there in case I screw up. And I will call that Green River. Green River in class base. Hopefully it can handle a file name that long. So now you see up here, it's created our base file. Right now, all that has is this pretty picture in it. If we want to add an image, we can go to background images, go back to the data, choose open, and there's our background image. I don't find it super useful, but I guess it has some utility. We look at the background image, if we're going to get fancy, which we will later, and maybe consider this area as a flow area. The background image to me suggests that clearly it does overflow that place, but it's mostly an island. And so these light blue dots there are not reflective of perennial stream flow. I'm going to turn off the background image because right now we're wasting space on my computer's limited memory. So we've basically gotten to here, page 2 of 40 in the tutorial. I don't know what that does. You don't have to do that anymore. And this particular interface has been replaced with this object browser. The data exploration tools no longer exist as described here. So you can't do these cool quasi 3D renderings. You can mess with graphics, but we'll skip with that. We've just done the equivalent of import ancillary data image. I did that by going to background images. I right-clicked and add image, or you can go up to File, Import, SQWhat, and background image is an option. Now we get to the important work. We have to build the computational mesh. And so what we're going to want to do is we want to build a computer mesh. In the old interface, we had to turn on grid and input conditions and create the unstructured mesh tools. In this one, okay, I'm going to try to hit the same shape that the authors have here. So that's why I have that kind of right there. It doesn't have to be exactly the same, but it'd be nice if I can get close. So now I want to go to grid, and we have to select an algorithm. So we'll select an algorithm, and our choices, there's many of them, are create grid from polygon shape. So that's the one we're going to use because it's the only choice we have. And then it gives you a message box saying, please define the grid. When you're done, double click or press the return key. Don't take too long because you will forget these instructions. So you hit OK. And now we're going to try the grid. And they were pretty kind of loosey-goosey with their grid, if you ask me. And when I'm crossing what I think is the stream, I'm trying to hit it perpendicular. Okay, that's my polygon. It kind of looks like that giant log in space in one of the original Star Treks that was eating up planets, and they had to fly a broken starship into it and set off the matter antimatter and blow it up, and it burped. But in this case, it's just a polygon, and we're going to have the computer go ahead and produce a triangular network over that. So we can do refinements, and we can move points on the grid if we want. We'll look into that later on this evening. Actually, we'll look on that next time. Let's go ahead and create the grid. So I select create grid, and I'll take the defaults first. I'm not going to check these boxes. Then I'll go back and change them if I don't like the picture. Okay, so that grid has one big old triangle for this area, one for that area. That's not a very effective grid for this case. I think we need to do something a little bit more refined than that. So we'll go back to our create grid, choose yes, and let's go ahead and I'm going to make the cells 200 meters. So I'm going to let the cells get as big as a few acres, and we'll see what that looks like. Okay, now that's now got a lot of points there. We're going to go back and change that again. I think that was 200 meters square. Choose no. We'll go ahead and I will draw the grid again. And yes, it would be nice if actually, before I do that, let me count. 1, 2, 3, 4. I think I'll just stick with that. And I'll make it bigger. We're going to go with that one. That's going to be an inadequate simulation, but I don't want to get too many grid cells. Now is a really good time to save your work, especially if you've got a grid that you like. So I'll press save, and down here it tells us it thinks it successfully saved the project. We can test that conjecture. I'm going to do the unthinkable. Let's test if it saved the project. Sweet. Now let's continue on with our next step. So we've done the grid generation. I declare that I'm, oh, they said use 73 meters squared. I almost kind of want to do that, but I will save that for another time. And you can read a lot of this stuff on your own, so I'm not going to bother you. They do have a way of coming up with a reasonable guess of desired area. So in this case, if we want triangles 13 meters on an edge, we would choose an area of 73 meters squared. And to do that, we'll go like that, choose yes. 73, and I think what they use for minimum angles is 35 degrees. Oh, this thing's a piece of junk. It won't let me go bigger than 32. Okay. Wow. We'll go with their simulation. What the hell? Okay, so in theory, we have now generated a grid using the example. And our boundary condition, when we get around to it, is just going to be this portion right here, because there's no flow up in here or over in here yet. And you actually see another thing, this gray area here, I don't think that's a big triangle. I actually think that that is a rendering issue. Yeah, it's a rendering issue. And that's another thing that you would need to get comfortable with using, little hand doesn't work. Talk to the hand. Get comfortable with is knowing when it's doing a rendering issue or not. Okay, so we've pretty much followed their example to that point. We won't worry about moving cells yet. Let's now go ahead and get to the next step, which is skipping the island, going straight to boundary conditions. Okay, so here they mapped the ancillary set to the grid. I'm going to skip that until after I have supplied boundary conditions and roughness conditions and just do the mapping all at once, which again is that's an improvement over the older interface. I'm trying to center things. This is what I hate about their graphical interface, but at least I'm not writing code, so that's cool. So the next thing we need to do is oh, actually, we need to do the inflow boundary condition, which is going to be down here. So I'm trying to center this area so that I can zoom in and prepare my boundary conditions. So boundary condition, I've gone to the boundary condition option. I right-clicked on boundary condition. I'm going to choose add inflow. I'll give it some stupid name like in-class inflow. And we need to give it a value. I believe the example is 400 meters cubed per second. 400, there we go. So we want to do a steady state thing. This is what's interesting. To do steady state, we just put a 0. Let me check the editor, and it shows nothing. And we could go to another time. This is probably unnecessary. But there is our inflow boundary condition, not terribly interesting, but we'll go ahead and leave that, press the okie dokie, choose OK. And the only thing I did is I actually didn't do the damn condition. sorry about that. Let's try this again. Grid, boundary condition setting, add inflow. I've got to tell it where to put the boundary conditions. So I'm going to use just kind of the darker blue stuff. And the reason I zoomed in is I've got to be sure I don't miss some of the edges. So what I'm doing is I'm drawing a polygon that's going to represent the boundary condition. So there's my boundary condition right there. In class inflow. Edit the condition. I'll go back and add more time if I need to. So now the boundary condition is there. I'm going to zoom out and I'll navigate to the other end, which will be a fixed, a specified stage boundary condition. That'll be good enough. And where this gets exciting is when we're doing models where our edges have some curvature to it. And it's expecting a stage value, and I believe the value it's expecting is 1448. At least that's what I'm going to put in. Let's check that. $1,448. Choose the okie dokie. Choose OK. And now we've saved our boundary condition. For complex models, what I just did there might take a considerable amount of time as a human being. So when you've just spent a considerable amount of time in something that's untrustworthy, what do? Save it. Okay, I'll zoom out. And I'm going slower than I thought I would. We'll get the initial simulation done today. And then I'll show you an intermediate result. We'll pick up the lesson next time, and you all can catch up to what I have here. Next thing we're going to need are the roughness terms. I think we do that up here. We're going to add a polygon, and then we'll define roughness. So please define the polygon by mousing around. So I'm not going to be very fancy here. We don't have to do what I'm doing right now, which is to have a single polygon that's going to be everybody's roughness. We can break it up into sections to represent geometric changes, and we want to set 0.040. Save. Okay, so we've now got as far as the roughness input. At this point, we have what we need for a minimal model run. So now we're going to go to grid, and we're going to go to attributes matching, and we're going to tell it to match elevation. Oh, actually cancel that. We need initial. We're going to try something different. Attributes matching, elevation roughness, inflow, outflow, choose OK. Save. So going here to my downlooking thing, we've built the grid, we've put in the boundary conditions, we've put in the friction model, we've mapped the attributes to all those little triangles, and now we're going to try to get a simulation started. In that, we go into the calculation conditions setting. And we're going to do uniform initial conditions. Usually I do coverage polygons, but I didn't set any. So we're going to do initial conditions. And flow is from this side to that side. So I'm going to put -1 meter per second and roughly 1 meter per second for the average velocity, and I'll set the water surface elevation at 1,448 meters. And that's one way to do it. Threshold for wetting cells, I'll stick with the defaults. Solution parameters. I did this earlier today, and 1e minus 3 I think will stay stable. And here's how I do. I do my first 10 time steps. I don't really care about the plotting increment just yet. Allow large time steps, those won't get invoked. And then resistance coefficient is Manning, no culverts, no wind forcing. Save and close, save. And now we are ready to attempt a simulation. So we click on the run doodle, and it's going to tell us to save the project. We already saved it, but we'll go ahead and do it again because it's smarter than us. Okay, so we just did 10 time steps. And what I look for in these initial ones are the size of these numbers, especially the ones that have negative exponents. I'm making sure they don't get too small and negative, because it means that the solution will go unstable before I get done. So I'm happy with that. I'll be careful here. You got to be careful with closing stuff, that you close the right thing. We can look at the output from that, although it's not going to be very interesting. We could do something like, we could turn on the flow depth, and so the flow depth is rendering anything that's not purple has water in it. So we can see the water pass. We see this part right here. Actually, that's blue and green. That's got more flow depth than I thought it would. We also can look at, let me turn off the depth, look at the velocity magnitudes. Whatever they are, they're around mean value of 1.3-ish everywhere. If we go ahead and do the velocity arrows, I'm just going to warn you, your eyeballs are going to get surprised when I click on this, because the arrows, the initial rendering, are way too big. So those are the velocity arrows. And if we go to the property of the arrow, we can rescale them. I think that'll probably be good enough. And as I zoom in, you see that they're all pointing to the left and pointing to the up, pretty much a 45-degree angle, and they all have the same magnitude. Now, why is that? That's because those were the initial conditions, and we ran like 3/1000ths of a second of simulation time. There's no time for anything to change. So save that. So now we have a place to start from. It appears that we have a working model. Let me save this again, because I just don't trust it. Okay, so we've now saved it. I'm going to open simulations I worked on earlier today. And you're going to have to take it on faith that the reason I'm doing it is because if I were to set this one up to the same simulation parameters, we could end class, we wouldn't come back for another half a day because these take a long time to run. So I'm now going to open my projects. I'm going to do run number 2, which I think is my most refined one. So there is one I did earlier today. Not sure how well you can see that on the screen. So this one has a whopping 100 seconds of simulation time. And there is what the instantaneous velocity field looks like. We could put in, what would be interesting? Flow depth or water surface elevation. So there's the water surface elevation. There's almost no resolution in here. That wasn't that good. There's our flow depths, and we can see that the flow is deep, kind of right along that channel. And what I think is interesting is we have circulation here, right where the flow hits the leading edge of that island and starts to get some swirly things. They're not very high velocity per se. We have a swirly thing here, and I think there's one little gyre right there. Let's go ahead and put the background image on it. And I'm going to turn off the depth. And unfortunately, what I wish they would plot is something called the curl. Because the curl, we could see what the swirly things look like, but they don't actually have anything that's close. I don't think the divergence is going to, yeah, it doesn't give us the information. So as we move around here, we see there's swirling as it's getting up to this part of the island. And there was a little swirl right in here. And there is a circulation actually around this little teeny island. Remember, the flow depth is pretty shallow right in this region. And that is an introduction to the storm model. Are there questions? Because we're almost done for the night. So what I'd like you all to do for next time is try to replicate this tutorial. I will put these, I've never tested if this will actually work, but I will put my in-class project file up onto the class server. So if you want to download it and try to go from the project file, you can. I don't see any downside to doing that. I'll also put these other project ones, but you really should build one yourself from scratch. Things that'll go wrong when you build it from scratch. You'll forget something, bugger up a boundary condition, or get something out of order, and when you reload the project file, you didn't save your work, and you'll have to recreate portions of the initial project. And that is it's frustrating, but I've had to do that a lot. It's just something you have to live with. If you accidentally don't change it as an IPROJ file, whatever the extension is, an IREC project file, you actually can save it as various ASCII files, because that's actually all that's in it. It's possible to rebuild an entire project from all these files, but it's a pain in the butt, especially if you forget one when you're trying to reconstruct it. So we're better off saving it as a full project file. All right, so that is your assignment, and that will get formalized in a proper homework assignment coming up next week. I'm going to ask you to reconstruct the tutorial, so you might as well get started. So try to do what I did, and then if that goes well for you, go back to the written tutorial, and you'll have to reverse engineer how to put the island in. Because as I said, the documentation has not kept up with the software. And so while it tells you what to do, none of the various things that it tells you to click on exist anymore. So inserting the island is going to take a little bit of reverse engineering. And there may well be another documentation I haven't found that tells how to do that. So I want to get to the island. There we go. It's going to be somewhere in the grid generation part. Right here in the grid creating condition, it looks like you can add a hole and add refinement regions. So that's where you will reverse engineer to try to add the island. Okay, we'll leave that with a velocity magnitude picture. And we'll turn on the background image and we'll make it big. And that is your first introduction to real two-dimensional fluid flow surface water modeling. I hope you find it cool. This is like the ultimate video game because of the frequent game over. Let me go back to the original one. I'm going to go ahead and start the in-class one. I'll show you what I mean by why. I'll show you why I went to the trouble to pre-run some stuff. Okay, so there's the one that we were working on a few minutes ago. And when we change our calculation conditions to something meaningful, do like 100,000 simulations. We'll plot every, that'd be 100 plots. Yeah, we'll go with that. I'm about to start the simulation. The solver monitoring window comes up. And each line of this is the time step, and I just told it to do 100,000 of them. And if I actually want meaningful results, sometimes I go to several million. We're at 2,000. So we're not even, we're at 4% completion. I'm not going to make you wait out the 10 or 12 minutes it's going to take. So that's why I do those initial short ones. And one thing that is useful about all these numbers rolling by on the screen, ones you want to be concerned about is these e to the fifths and e to the minus fifths. So if this is going to go unstable during the simulation, it'll be, in this case, one of these two columns is going to drive it unstable. And if I look at the second column, I'm getting 153, 152, 151, 150, 149. It looks like that number is getting slowly smaller. And the next column, 36, is also getting slowly smaller. The other ones are changing, but they're not an alarming value yet. A 32-bit computer, when those numbers hit like minus e to the minus 12 or minus 13, at that point they're garbage in the program will fail. And ironically, the program ran just fine up until failure. You're supposed to be able to restart from a prior run, but I've been unable to get that feature to work. And either I'm clicking on the wrong things. There's no programming from my part. I'm just operating an interface. We're driving a bus here. So with that, I will bid you all a good night. I hope you have a wonderful weekend, and hope the weather gets warmer, because I don't want it to be chilly and cold. I'll see you on Monday. Have a great weekend.
You too.
Okay, bye-bye.
Good night. Thank you.
Good night. Bye.
Good night.